Hello everyone, my name is Nikhil Dalvi and my group mates are Darshan Lakde and Ishan Patil. I am going to present the presentation on implementation of FIR filter using DSP processor, and our project guide is Nutan Bansode madam. These are our outlines. Problems First is problem statement or objectives, second is introduction, then FIR filters, then different types of windows, implementation and results, formulas and calculations, conclusion and references. These are the problem statement. To implement an FIR filter using TMS 320 F28335 DSP processor, and our objectives are to study the different types of windows and to analyze the noisy signal, to calculate desired frequency response coefficient, and to calculate windows coefficient, and analyze the output signal, and to design the design and implement the filter using dedicated DSP processor. uh, uh, this is our introduction. In nature, no signal is totally clean. Each signal has one or more types of distortions. Before they may be utilized for application, this distortion must be eliminated. This is where filters are used. Filters allow only specific band frequencies to pass through them and attenuate all other frequencies. There are different types of filters categorized on the basis of band of frequencies they passed. Low pass filter and frequencies below the cutoff frequency, and high pass filter passes all frequencies above the cutoff frequency. Many input signal can be filtered by one digital filter without replacing the hardware. Digital filters have characteristics like linear phase, which is not possible to obtain in case of analog filters. In this implementation, we are going to use TMS 320 F28335 DSP processor. It is a floating point processor, which is well suited for performing very heavy calculations. This is FIR filters. FIR stand for finite impulse response. These filters are called as non-recursive filters because they do not use the feedback. In order to design such filters, various Windows functions are available. The windowing method requires minimum about two computations effort, so it is simple to implement. Also, for the given window, maximum amplitude of ripple in the filter response is fixed. Thus, the stop band attenuation is fixed in the given window. And next is, while designing a particular filter, first the specification of the required filter have to be defined. This specification may vary depending on application of the filter. Only if we know the required frequencies to pass through can be move ahead. Once the cutoff frequency is known, we can move ahead and calculate the desired frequency response. Taking inverse Fourier transform of this response, we can calculate H. In this, N stands for order of filter, which will be mentioned in the specification. Substituting different values of N will get different values of H of N. These are the different type of windows. First is rectangular window. It is the simplest window function available. Its magnitude is 1 for the range n equal to 0 to m minus 1, where m is the length of the filter. The equation is wr equal to 1 for n equal to 1, 2, 3 up to m minus 1. As second is Hanning window. The Hanning window is named after its inventor Von Hahn, and the shape of one cycle of cosine wave with the one added to it, so it is always positive. Its equation is Whn equal to 0.5 in bracket 1 minus cos 2 pi n by n minus 1 bracket. Uh, the third is Hamming window. This is another window function popularly used. The Hamming was named after R.W. Hamming. It was recommended for smoothing the uh, truncated autoconvergence function in the time domain. It function is given as WHM equal to 0.54 minus 0.46 in bracket cos of 2 pi n upon n minus 1. uh, Fourth is Blackman window function. In Blackman window function, we find the more additional term in comparison with Hamming and Henning window. Because of additional cosine term, side lobes are reduced further. Window function for Blackman can be given as WB equal to 0.42 minus 0.5 cos of 2 pi n into n minus 1 n minus 1 into n minus 1. These are our implementation results. The first is waveform of input noisy signal. Taking Fourier transform of this signal will give us an idea of frequency present in this signal and its magnitude. Owning the Fourier transform plot of CCS, we can directly plot the Fourier transform of noisy signal. Second graph is a frequency plot of input signal. From this frequency plot, we can analyze that our noisy signal has roughly four frequencies components. The frequency plot has frequency in hertz on the x-axis. Third graph is of waveform of output signal. Once output signal has been calculated, we plot it using the graph features of CCS. Uh, we find that the output is sinusoidal wave corresponding to fundamental frequency, and the fourth output is frequency plot of output signal. Now we plot the frequency plot of the output signal. It shows that the filter has only the fundamental frequency and it has heavily attenuated res, uh, res, reset. Then frequencies. The above steps should the designing or low pass filter with a cutoff frequency of 50 Hz. So these are the formulas and calculations. These are the steps. Now the same steps will be followed as followed for low pass filter to get a high pass filter or cutoff frequency 50 Hz. So this is the conclusion. Efficient hardware implementation of filter using the digital signal processor is done. From the result, we can conclude that the final output signal has only the fundamental frequency. All the other frequencies have been heavily attenuated through the filter algorithms. It is also observed that DSP reduces the tedious calculation and computes the convolution very quickly and saves a lot of time. A digital signal processor has a wide range of uses, and one of them is for creating filtrations. The DSP can filter real-time signal using ADC and DAC that and output output the processed result on the oscilloscope. These are the references. Thank you.